Welcome to qnawire.
This is problem number 20 of chapter 23. For this problem, we have a soap bubble here. This rectangle is going to be the representation of that soap bubble film, and there's light coming in here, normal to the surface of the soap bubble, and the question asks, what is seen on this side of the soap bubble as the bubble thins out and eventually pops? So we have light coming in, like so. A portion of it is going to be reflected, and then the rest gets transmitted. And then from that transmission, then it hits the boundary again, and then it comes out, hits this boundary, and then it comes out like this. The question is asking what is seen on this side of the soap bubble. So let's go ahead and make some annotations here. We start in air with a refractive index of 1.0. We are in the bubble, so N, this can be an F for film, and we're gonna assume that this is greater than the refractive index of air, and then here on the other side we also have air. The thickness of the bubble here is T. For us to see something on this side of the bubble, these two rays are going to have to constructively interfere. So we're looking for constructive interference. As light strikes the boundary, it's going from a lower refractive index to a higher one. So we're going to experience a phase shift here at this reflection of 180 degrees. So a phase shift of 180 degrees can be symbolized as a path length difference of lambda over 2. So as the light comes in and it gets reflected the first time, it gets shifted by 180 degrees because it's going from a lower refractive index to a higher one. That shift of 180 degrees is the same thing as a path length difference of lambda over 2. The light continues and gets so that one portion gets reflected, the other portion of the light gets transmitted into the film, and its wavelength changes because it's in a different material. The frequency stays the same here and here, but the wavelength changes. The path length difference, it's going to be 2t because it comes down and it gets reflected again. So 2t, one t coming down, another t coming up. When it reflects here at this bottom portion, it's going from a higher refractive index to a lower one, so no phase shift takes place. And then as it comes out of the bubble, again it's going from a higher to a lower, so no phase shift takes place. So our net path length difference, let's call it delta, it's going to be delta reflection due to this first reflection right here, plus delta t due to the path length difference as light goes through the bubble. For constructive interference, this must come out to m lambda, or an integer multiple of wavelengths for constructive interference. Okay, since delta reflection is lambda over 2, let's go ahead and write that out. Lambda over 2 plus delta t is going to be equal to m lambda, where m lambda is an integer multiple of wavelength. Delta t must therefore be an odd integer multiple of half wavelengths, because that's the only way that I can that's the only thing that added with half a wavelength is going to give me an integer multiple of wavelengths. Another way of saying that is if I have 1/2 plus what? 1/2 plus x is going to give me some whole number, some whole integer, let's say 5. X must be an integer multiple of half wavelengths. So that's the argument here. We're going to set delta t equal to an integer multiple of half wavelengths. Now this can't be an even number, so if m was equal to 2, 2 over 2 is lambda, so lambda plus lambda over 2, that's not going to give me a whole number of lambdas. So therefore, when we're defining delta t in this way, we have to be careful and change the index here for m. M is going to be odd integers. Therefore, m times lambda over 2 is really odd integer multiple of half wavelengths. So if delta t is an odd integer multiple of half wavelengths plus lambda over 2, sum together, that results in a path length difference that results in constructive interference. Okay, so delta t is equal to 2t. And this is going to be equal to m lambda over 2. Now, the other thing that we have to be concerned about is that this lambda is not the lambda of the light in air, it's the lambda of the light in the film, because that light is in the film for this delta t. So how do we rewrite this lambda film in terms of the regular lambda? So the formula is written with respect to the refractive index, and film is going to be equal to the speed of light in vacuum over the speed of light in the film, and the speed of light is lambda f. Let's go ahead and solve for V film here. We see that V film is equal to lambda f over n film, but velocity is written as lambda of the film times f, because the frequency is determined by the source. So we cancel out the f's, and here we find that lambda film is equal to lambda over n film. And we're going to go ahead and grab this value and plug it in here. This expression tells us that the thickness of the film is proportional to the wavelength that constructively interferes upon the reflection here. So here we go ahead and solve for t. The thickness is proportional to the wavelength that constructively interferes on this side. So as the film thins out, as t goes to 0, so let's say as t goes to 0, as the bubble thins out, the wavelength that yields constructive interference must also decrease. So lambda decreases. As the bubble thins out, lambda decreases. So if we are up here viewing the bubble as it's thinning out, first we're going to see reds, and then as it gets thinner and thinner and thinner, then we're going to see green, then blues, then violets. And then it's going to pop, and then we're not going to see anything. And we're not going to see any colors. So the thickness as the bubble thins out, the lambdas, the wavelengths that yield constructive interference, are going to be the smaller wavelengths, so that corresponds to colors like violet. And if we initially start at red, we're going to go red, orange, yellow, blue, and then violet. So let's draw a graph with the intensity versus the disturbance here. So let's suppose we have a graph here measuring thickness, and then this is measuring, let's say, the intensity of a particular color. When, according to this expression, if we have a thick bubble, the thicker wavelengths are going to be visible. So for thicker bubbles, let's say we start here with red, and as the bubble thins out, red, we're going to see less and less and less until we don't see it anymore. As the bubble starts thinning out, the light that causes constructive interference is going to be that wavelength with a lesser value than the wavelength of red. So let's say orange, for example. So orange is probably going to be somewhere up here, and then it's also going to thin out, and the intensity is going to approach zero as the bubble thins out. And then eventually all that we're going to be left with is the violets here at this end. So let's say we had some violets here. Constructive interference occurs as it's thinning out, and then if the bubble continues to thin out, there will be no light on this side. You won't see anything. So what you would see is red, orange, yellows, greens, blues, and then finally the last color you would see is violet, and then the bubble will pop. So it's based on this expression here, where the thickness is directly proportional to the wavelength that constructively interferes. In other words, what you see on this side. This concludes problem 20.